This conference will now be recorded.
Hello everyone. Today we're starting a new chapter, aldehyde, ketones and carboxylic acid. Today we'll discuss carbonyl group, structure of carbonyl group and nomenclature of aldehyde and ketones. Aldehyde, ketones, carboxylic acid, in all these three types of molecule, one thing is common and that is carbonyl group. So this group is C double bond O and carbon will have two more bonds and both sides there may be any substituents. So this is the carbonyl group. So the class of organic molecules, they contain carbon atom connected to oxygen atom by a double bond and that is known as carbonyl group. Now this carbonyl group, the carbon that is present, that is trigonal planar. That means it remains in a plane. And why it is trigonal? Because that depends on hybridization. That will go into details in the structure slide. That is when we will discuss the structure of carbonyl group. But it is trigonal planar because of its sp2 hybridization. Fine. And it can be attached to two other substituents both sides, and that will lead to different types of subfamilies. So depending on what type of groups are present on both sides of the carbonyl group, there may be compounds aldehyde, ketones, and obviously there are some more variety that are based on carboxylic acid and their derivatives. Fine. So aldehyde is when one side we have alkyl group or aromatic group, other side one hydrogen must be there. But when it is ketone, both sides there is no presence of hydrogen, and both sides we have some alkyl group or aromatic group. It may be same or it may be different. And when it is carboxylic acid, one side there is alkyl group or aromatic ring, other side there is OH group. Now as it is mentioned that aldehyde, ketones, carboxylic acid, and not just ester, carboxylic acid and its derivatives. Ester is one of the derivative of carboxylic acid. So when we are saying derivative of carboxylic acid, it is actually this OH group that is this OH group that may be replaced by different other groups. Okay, so all of them together collectively we call it derivatives of carboxylic acid. Here we have some examples of derivatives of carboxylic acid. So groups that will replace this OH that are present in the first column. It may be chloride, NH2, OR prime, or OCOR. It is actually like this, OC double bond OR. So depending on what type of groups are replacing OH, we have different names for the derivatives of carboxylic acid. Here you can see the general structure in the third column. Second column we have the names, and the last column you can see the actual example. So when it is OH replaced by Cl, we call it acid chloride. Example, acetyl chloride. Here R group is methyl group. Then if OH is replaced by NH2, then this group is known as amide and we call it acid amide. Example, acetamide. If it is replaced by OR prime, now this is ester group, so we call it ester. And example, see here R group is methyl and R prime group is also methyl. Then acid anhydride. Now if the OH group is replaced by RC double bond O and oxygen, that will be called acid anhydride. Example, acetic anhydride, where these R is still R, but the other R group, that is methyl. So these are the different derivatives of carboxylic acid. But before going to carboxylic acid, first we have to finish aldehyde and ketones. And after finishing this, there will be discussion related to carboxylic acid. Structure of carbonyl group. So this carbonyl group that is present in aldehydes, ketones and also carboxylic acid and their derivatives. So what is the structure of carbonyl group? When we are saying structure, it means what is the hybridization of carbon and oxygen in this group, whether it is planar or not, then how many pi bonds, lone pairs are present or not. All these things will be discussed under this topic, structure of carbonyl group. So as it is C double bond O and oxygen, we have two more lone pairs. For carbon there will be two more bonds and there may be different substituents. So what is the hybridization of carbon? Let's see first. Carbon, if we consider from which group it is from group 14 and second period. Now group 14 means its valence electron will be 4. So it is actually 2s2, 2p2. 2s2, 2p2. Now this is written in this way. 2p, 2 unpaired electron, 2s, 1 paired electron. But this is ground state configuration. When it is in excited state, you are providing energy. Now what will happen? This pair will be broken and one of the electron from 2s2, now it will be shifted to 2p. Fine. Now we have 1 electron in 2s and 3 unpaired electron in 2p. So now it is 2s1, 2p3. This is excited state. Only when you provide energy it is possible. And carbon, it is sp2 hybridization. sp2 hybridization means there will be 1 s and 2 p orbital. That means 1 s, 2 s actually, and 2 electron from p. This will be hybridized together and there will be formation of total 3 sp2 hybrid orbitals. So these 3 are sp2 hybrid orbitals. Now here one thing you have to notice. This electron is not taking part in hybridization. This is out of hybridization. It is unhybridized p orbital. So this electron that is present in this unhybridized p orbital, that will actually take part in pi bond formation. And all the electrons that are present in sp2 hybrid orbitals, they will take part in sigma bond formation. 3 sigma bonds will be there for each that is sp2 carbon and 1 pi, and there is no lone pair. Fine. So this is the hybridization for carbon. It is sp2 hybridization and that is why it is diagonal planar. What about oxygen? Hybridization of oxygen. Oxygen, it has 6 valence electron. It is from group 16. And when we say group 16, you have to consider the last digit for the group. So for p block, so 6 valence electron and it is 2s2, 2p4. In case of carbon, we have seen it is 2s2, 2p2, but now it is 2s2, 2p4. 2s2, 2p4, there will be again hybridization. Now when we are saying hybridization, one that is the 2s, only one orbital present, and 2 p orbital that will take part in hybridization. So this will be the hybridization, and this one of the p orbital, not necessarily it is pz, it may be x or y also, but one of the p orbital, its electron, it will not take part in hybridization, and this will be basically involved in pi bond formation. Okay, so we are having here total 3 sp2 hybrid orbital. Fine. Now if we look at the carbonyl group, you can see there is 1 sigma bond, 1 pi bond, right? So oxygen will form 1 sigma bond with carbon, and carbon is also forming 1 sigma bond with oxygen, and carbon is forming 1 pi bond with oxygen, and vice versa. So this p orbital, which is not taking part in hybridization, that is actually responsible for pi bond, and also this p that is responsible for pi bond. And oxygen, it has only 1 sigma. So this 1 sigma bond, that will be by this sp2, and the other 2 sp2 where paired electron present, that will be actually lone pair. So 2 sp2 orbital, they will contain the lone pair of electron. So now we have individual sp2 oxygen, sp2 carbon, and we know that sigma bond is formed by head-on overlap. So this you can see this blue color, the orbital, that is actually sp2, and the red color, that is actually unhybridized, which is not have taken part in sigma bond formation. So this p orbital is basically this one. Okay, the red color. So there will be head-on overlap and sigma bond formation will take place, and for these two, this one is unhybridized p orbital for oxygen, and this is also unhybridized p orbital for carbon. There will be side-wise overlap and pi bond formation will take place. And you can also see these two, they are actually is one sp2, this is also sp2, that are carrying the lone pair, and for carbon, this is also sp2, this is another sp2, each containing single electron, So these two sides, there will be actually two more groups. So that is not written here for simplicity, but two more bonds will be there. Both side it may be alkyl group, hydrogen, OH, NH2, whatever, depending on what type of compounds you have taken. Aldehyde, ketone, carboxylic acid, its derivative. But important thing is carbon will have two more sigma bonds with these two sp2 hybrid orbit. So this is the CO double bond picture. The blue color bond, that is sigma bond, and the red color is pi bond. You can also consider the picture in this way, where you can see this is sidewise overlap, this is sigma bond, these two are lone pair for oxygen, and both side of carbon there are two groups, and which group, that is not mentioned. But this is pi bond, the purple color, and yellow color is sigma bond. You can also draw the picture in this way, so that you can understand that why carbon it is having trigonal planar configuration. So in this picture it is completely clear. So CO bond and these two groups, sigma bond, suppose I am writing here R group or R group, they are actually present in the plane. So you can see this square plane, and this p orbital, that is actually perpendicular to this plane. So this angle is actually 90 degree, and as we know that the angle for sp2 hybrid orbital, it is 120 degree. So this angle 120 degree, this is also 120 degree, this is also 120 degree, but all these bonds, they are present in the plane. Only the p orbital is perpendicular to the plane. So this is actually the sigma bond, and sidewise overlap, that will form the pi. Now the pi bond, sometimes you will see this type of resonance, where in the first picture sigma and pi bond you can easily identify separately, but the pi bond you can also break it, and when you are breaking the pi bond, you have to place positive charge over carbon and negative charge over oxygen. And if you are breaking the bond partially, suppose you are breaking the bond like this, see, this is sigma bond, oxygen, and the bond in this picture it is fully broken, but suppose I am writing it in this way, dotted line, that means it is not fully broken, it is just broken. So under that case, you cannot write full charge, then you have to write partial positive charge, partial negative charge. But when you have broken the bond fully, then fully developed positive charge and negative charge is present. And if you are thinking why positive charge on carbon and oxygen over oxygen is having negative, why not the reverse? It is because oxygen is more electronegative, so it will have the negative charge. Okay, so these are the different forms in which carbonyl can be drawn. This is the normal picture where sigma and pi bond you can see. Here pi bond is fully broken, and there is positive charge, full positive charge, full negative charge over carbon and oxygen respectively. But if the bond is partially broken, now there is partial positive charge and negative charge that you can see in this picture. Fine. So that is the structural information about the carbonyl group. Next we will start nomenclature of aldehyde and ketones. So we will see first separately the rules for aldehydes. These aldehydes may be having open structure or ring structure. After that, there will be nomenclature for ketones. That is only keto group present in the molecule. What will be the rules? And after finishing that, you will also see that when both the groups, suppose aldehyde, ketone, both the groups are present in the same molecule, then how to do the nomenclature, that we will also see. But first we will start with nomenclature of aldehydes, where only aldehyde groups are present, not any other group. Aldehyde, they take their name from their parent alkane. Now parent alkane means, suppose 2 carbon alkane, it is ethane, 1 carbon, it is methane. So we know that when it is alkane, we use the suffix ane. But when the parent alkane, one of the hydrogen, now it is replaced by COH, that is C double bond OH. Now what will happen? Now the E that is present at the end of ANE, that will be removed, and this E will be replaced by L. So E is removed from the end and is replaced with L. Okay, we'll also see the example. The aldehyde functional group, that is C double bond aldehyde functional group, means this group. This carbon will be given number 1 location, but that you don't have to mention in the name. That is already understood, because this is the rule. It is already 1. We know that. Everyone knows that. So you don't have to specifically mention that. Okay. So let's see some examples. The first example is 4 carbon. I'm writing 1 from here because carbonyl carbon of aldehyde group, that will be given number 1, 3, 4. So it is 4 carbon. So if it is simple 4 carbon alkane, what you will call it? You will call it butane. But now instead of writing butane, it is not ANE. Look at the spelling, ANE. Now it is ANAL. As it is mentioned, E will be replaced by AL. So that is clear in the name. Another example, pentanal, 2, 3, 4, 5. So if it is simple hydrocarbon, 5 carbon chain hydrocarbon, it is pentane. But now ANE, just remove the E and write AN. And the names that you are seeing in blue color in the bracket, that are actually the common name. And the names in the black color, that are IUPAC name. So for common name of aldehydes, that start with common parent chain name. So as it is 4 carbon, the first example, so it is starting with but, but you have to end it with the suffix aldehyde. Fine. Though common names, even if you do not remember the rules, that is fine. But IUPAC rule, that you have to remember, because common name normally we use only for those aldehyde ketones or any carboxylic acid and their derivatives, if the structure is very simple and small molecule. For large structure, complex structure, we do not use common name. Another example, it will be 1 carbon. This is 1, 2, 3, 4. So this methyl, that will be treated as substituent, and the substituent position is at 3 carbon. So that is why it is 3 methyl butane, but we will not write butane, we will write butanal. Here we have methyl substituent. When the CHO functional group is attached to a ring, so these 3 examples that you have seen here, they are open structure, there is no ring. But suppose the CHO group is present, that is attached to a ring structure, then the rule is different. When it is open structure, the first point it is mentioned that E is replaced with AL. But now the difference is, you have to use the suffix carbaldehyde, not L. And the carbon attached to that group will be C1. So when it is open chain structure, the carbonyl carbon of aldehyde is given number 1. But when it is ring structure and the CHO group, suppose you have any 6-membered or 5-membered ring, whatever, and you have CHO group attached. Now this carbon is not 1, but the carbon with which this carbon is attached, that is actually 1. So here the rule is completely different if you compare with open structure. So here we have 5-membered ring and CHO group is attached with this 5-membered ring. This carbon will be carbon number 1. And next you will move towards this side, because if you move towards other side, that is not accepted, because in that case methyl will be given very high number. So that is why this path is favored. So after this CHO group, if you move to next carbon, at 2 position you have methyl group, and these 2 groups CHO and CH3, they are opposite to each other, so that is why the name is trans 2 methyl. Then you have to write the ring, that is how many carbons are there in the ring, it is 5 carbons. So you have to simply write cyclopentane. Just forget about everything. If it is simple 5-membered ring, what you write? You write cyclopentane. So just write that, but before you have to put the, if there is any substituent, in our case it is 2 methyl, and after this term cyclopentane, you have to end it with the suffix carbaldehyde. Fine. So when the CHO group is attached to a ring, the suffix carbaldehyde is added and the carbon attached to that group is C1, not the carbonyl carbon is C1. Similarly, next picture we again have a 5-member ring. This is CHO group, so this will be carbon number 1. Now you will move towards this direction, because if you do so, bromine, it will get minimum number, as minimum number as possible. So 3, 3, 2 times you have to write because 2 bromine substituents are there. Dibromo, then cyclopentane. So just like the before example, cyclopentane you have to write. But before that, if there is any substituent, just mention that. If there is no substituent, you don't have to mention anything. In that case, it will be cyclopentane carbaldehyde. Okay. And after writing cyclopentane, carbaldehyde, that term is common. So whatever is the size of the ring, you always have to end the name with carbaldehyde. Okay. What about the rules for ketones? Ketones take their name from their parent alkane chain, and just like you have seen in case of aldehyde. But now the ending E is replaced by ONE. In the previous case, you have seen it is replaced by AL, but now it is replaced by ONE. And what about the common name? When it is common name for ketones, they are simply the substituent groups that are present both sides of the carbonyl, because the general structure of ketone is R, CO, R prime. R prime and R, it may be same or it may be different. So you have to mention the name of these two groups alphabetically, and then you have to write ketone. If it is very simple structure, you can use common names, but not always. When the structure is very complex, large structure, common names are not used. But for simple ones, we do not use IUPAC, mostly common names are used. Even if when you will get problem, you will see the common names are there. So that is why it is important for us to remember common names for the simple ketones and aldehydes. Here you can see the third point, simple ketones are known by their common names. So the first, that is the simplest ketone possible. What is the simplest ketone possible? It is obviously this one. Because both sides you have to place at least one carbon. You cannot place H. When you are placing H, it is no longer ketone, it is aldehyde. So you have to place one carbon. So this is the simplest ketone possible. Okay. So the common name we use for this acetone, but actually the name, if you consider IUPAC, it will be propanone, because here total number of carbon 1, 2, 3. But one thing interesting, sometimes it is also written as that is 2-propanone. Sometimes it is also written like this. But even if you don't do so, then also it is fine. And the reason is, whenever you have 3 carbon, obviously in the middle carbon you will have carbonyl. You cannot place carbonyl in the terminal carbon, because in that case it will be aldehyde. So that is why even if you do not mention 2 before propanone, then also it is fine. You just have to check when, suppose you cannot see the structure right now, just forget about the structure. You have only this name and you have to write the structure. So you just have to check whether you can draw the structure. And just by looking at the name propanone, yes, you can draw the structure. That means even if you do not write 2, that is also fine. Then the next structure, here remember it is acetone, which is the common name. Next structure we have one side phenyl group, other side methyl group. Now it has common name methyl phenyl ketone. As it is mentioned, alphabetically you have to use the substituents. So M comes before P, MNOP. So that is why methyl is written first, then phenyl. But there is another common name, which is, so this name is mostly used. You will hardly find the name methyl phenyl ketone. Mostly this molecule is known as acetophenone. This is the mostly used term. And what about the IUPAC name? IUPAC name, if you consider, now first you have to check in the longest chain how many carbon. Now here phenyl you have to consider as substituent. So if you consider as substituent, then this will be carbon number 1, this will be carbon number 2. So it is 2 carbon chain. And in one position you have ONE. So one position you also have phenyl substituent. You have to start with the substituent, one phenyl, then ethane, one more. Fine. One phenyl ethane. Ethane is because it is two carbon chain, and you have to end it with on. One position there is on. That is why one hyphen on. Next example, we have phenyl group both side. That is why common name diphenyl ketone. It is also another term is used, benzophenone, and that is the most common name used for this one. But you can also write the IUPAC name, which is diphenyl methanol. So why diphenyl? Because you have two phenyl group both sides, so that is why diphenyl, and it is single carbon, so that is why methanol, and you don't have to mention the position because it is single carbon. No need to actually it is not possible to mention the number, so that's why number is not there. Now look at the next one, fourth example, ketone. This is one, that is number 1, 2, 3, 4, 5. If you are thinking why not the opposite numbering we have done, that why not the numbering is not starting from left hand side. If you are starting from left hand side, ketone will be, that is this carbon, it will have 4, which is not correct. You have to do the numbering in such a way so that carbonyl carbon is getting as lowest number as possible. So that is why numbering is starting from the right hand side carbon, because in that case keto carbonyl will get the number 2. So it is 2 pent, because it is 5 carbon chain, pent, but normally what we write, pentane, TANE, but now we have not written E, we have written TAN. After that, in place of E you will write ONE, as it is mentioned in the first point. But common name is methyl propyl ketone. Why methyl propyl ketone? If you look carefully, one side you have 1 carbon and the other side you have 3 carbons. So that is why methyl group and propyl group, but M comes before P alphabetically. So that is why methyl propyl ketone. The next structure, 1, 2, 3, 4. So we have one methyl as substituent, right? So 3-methyl 2-butanol. First you have to write the substituent if present. If not present, like the previous example, you don't have to mention anything. And then 2-butanol, because 2 position we have the one, but it is not butane, TAN, no E, it is ONE. And what about the common name? So when it is common name, in this ketone molecule, one side we have 1 methyl, that is 1 carbon, which is methyl group. Other side we have isopropyl group. It is not just 3 member, because in the previous example also it is 3 member. We have written propyl, but it is not linear chain, there is branching, and this type of group is known as Me2CH. It is known as isopropyl. So the name will be methyl isopropyl. Okay. Then 3-hexanol. So numbering we will start from this side, 2, 3, 4, 5, 6, because if you do the other way, follow the other way, ketone will be getting, the carbon will get number 4, but in this case it is 3, that is why this is correct. And the total chain, it is having 6 carbon, so that is why 3-hex, not hexane but hexanol. And what about common name? This side you have 2 carbon, the other side you have 3 carbon. So ethyl group right hand side, methyl group, sorry, propyl group left hand side. So that is why the name ethyl propyl ketone. Naming aldehydes and ketones in the same molecule, that means now you will have the CHO group and the keto group in the same molecule. Now what will be the number? Now when 2 groups are simultaneously present, obviously you have to check the priority. So we know that not just for aldehyde and ketones, whenever you will have 2 or more functional groups, suppose you have CO2H OH or OH CHO like this, then one group you have to give more priority, and the group which is getting more priority, based on that group you have to uh, write the prefix, fine. And the other group which is having less priority, that will be considered as substituent. Now among aldehyde and ketone, aldehyde will get priority. So aldehydes have higher priority than ketone, so it will be having the suffix, and the prefix that will be for ketone. Now when aldehyde, it is used as suffix, obviously al term that will still be used. But for ketone, we know when it is having the highest priority, we use ONE as suffix, that you have already seen in the previous slide. But now it is not suffix, now it is prefix, that is the lesser priority group. So that is why now it will have, you have to use the term for this ketone because it is the next priority, not highest priority, OXO also. And it is also not necessary to give the aldehyde functional group because this is the highest priority group. You don't have to put any location number. But for ketone, as it is the substituent, you have to give the location number. Because for aldehyde, as it is having the highest priority, by default it will have always number 1 position, the carbonyl carbonate. So separately you don't have to mention that. But what is the position of C double bond O of ketone? That you have to mention. First example, we have aldehyde group. So numbering will be started from here, 2, 3, 4 position you have ketone. But it is total 5 carbon, the chain number. So that is why it will be pent, but it will end with L. Pentane, what is the spelling? Pentane. But after N, we have not written E, it is Al. So same rule that you have seen in case of aldehydes. And here our position of ketone is 4, so 4 also. Next molecule, you have 2 keto group, 1 aldehyde, 1, 2, 3, 4, 5. And see, as it is mentioned that it is not necessary to give aldehyde functional group any location, so we have not given any location. Location is only for the oxo. At 3 and 4 position we have 2 oxo group, so 3, 4 dioxo. Then as usual, like the previous example, it is pentanal. Next we have 1, 2 position C, there is methyl group. 3 position oxo, 4 position. So total number of carbon in the longest chain is 4. So it will be butanal. But you have to use prefix, which is 2-methyl 3-oxo. Now M will be alphabetically, it is before O. So that is why 2-methyl you have to write first. It is not for substituent. It is not that 2 is less than 3, that is why it is written. No. M is alphabetically, it is coming before oxygen. So that is why it is 2-methyl first, then 3-oxo. Not 3-oxo 2-methyl. If you write so, it will be wrong. Okay. If it is dialdehyde or diketone, that is 2 aldehyde groups present in same molecule, 2 keto group present in same molecule, then what you will do? For dialdehydes, the location numbers for both carbonyls of the aldehyde group are omitted. So you don't have to mention the location of aldehyde, because see, when we are saying aldehyde, one side of the carbonyl, there will always be hydrogen. So this is one aldehyde, this is another aldehyde. So you cannot place, it is not possible for you to place carbonyl for aldehyde in the middle of the chain. It will always be at the terminal position. So these two aldehyde, it will always be connected like this. And here I have written it in general form. Here you can have 2 carbon, 3 carbon, 4 carbon, whatever. But the 2 aldehyde, they will always be at the end of the parent chain, terminal position. So that is, you don't have to put any number. The ending dial you have to write, because now it is not single Al. If you write, it will not be correct. There are 2 aldehyde groups, so that is why you have to write Di then L. Let's see example. Pentane dial. Okay. Why it is pentane? It is 1, 2, 3, 4, 5. And As I have said, terminal position aldehydes groups are present. You don't have to put any location number. It is simple, pentane. Now see, E is still there. So when it is dialdehyde, it is not that. In this case, what you have done, you have only one aldehyde. So it is pentanal. It is not you have finished the writing the name of alkane, pentane, then you are adding L. No, it is not like this. But in this case, when you have two aldehyde group, you have to write completely the alkane chain, pentane, TANE. Do not omit the E, and then dial. Similarly, when two keto group, now for two keto group, you have to put location number because keto group can be anywhere in the chain. Okay, it will not be a terminal. So 2 and 3 because it is 1, 2, 3, 4, 5, 6. Why not the other way direction I have done numbering? Because in that case it will be 4 and 5. The keto group it will get 4, 5. But you have to choose that numbering which is giving you as lowest number possible for the keto group. So 2, 3, longest chain 6 carbon, hexane. Write completely the term hexane. Do not omit it. After that write diol. So this is nomenclature when there are two aldehyde groups or two ketones. Now, all the examples that you have seen, all are open structure, not cyclic. But if it is cyclic, then that is cyclic aldehyde we have seen. But if it is cyclic ketones or diketones, then what will be the rule? So in cyclic ketones, the carbonyl group, that is the carbon of C double bond O, that will always be given number 1. Okay, and this number is not mentioned in the name unless more than one carbonyl group present. So when it is only one keto group present, you don't have to mention the name. Okay, rest of the ring is numbered to give substituent the lowest possible location. In the first example, you do not have any substituent, so no question of putting any location. So it is simply cyclopentanone. Cyclopenta, that is pentane, TANE. Just remove E, put ONE. Then we have in the second example, we have bromine substituent at 2 position. This is 1, this is 2. So 2 bromo, then cyclopentanone. So this part is same as the previous example, only you have to put 2 bromo extra. Then we have 1, 2, 3, 4. 4 position hydroxy group, 4 hydroxy cyclohexanone. So just like cyclopentanone, you have to write cyclohexane, remove E, put ONE. In the next example, we have 2 substituents, 1, 2, 3, 4, 5. Okay, if you move in this direction, then methyl will be getting number 3, bromine will be having 6. So 3 and 6, they are giving you high number. So that is why this numbering is correct. 2 position bromo, 5 position methyl. Bromo you have to write first because B comes before M. That is why. Then cyclohexanone. The prefix cyclo is included before the parent chain name to indicate that it is a ring. Now when there are 2 ketones, what will happen? When there are 2 ketones, both carbonyl need to be given a location number. So see 1, 2, 3, 4. This is 1, 2. 1, 2 cyclohexanedione, cyclopentanedione. Now one important difference you can see. These 4 examples, you have only one keto group. But these 2 examples, you have 2 keto groups. So when there are 2 keto group, now E is not removed. Try to understand the difference. Again, I am saying, when it is only one CO, and these 2 are 2 CO. So when it is 2 CO, it is not it is cyclohexane, write completely, then diol. Cyclopentane, write completely, then diol. But when it is only one carbonyl, it is not you are writing cyclopentane completely, then on. No. Now it is TAN, stop. Don't write E. write ONE. That is the difference when it is diketone and single ketone. So in this case, E is not removed from the end, but the suffix dione is added. So this is the difference. These 2 points are covering rules for cyclic and as well as diketones. Fine. Now some more examples we will see, and how here you will see individual columns are there for the prefix, then the root word that is used, and if there are 2 types of suffix are actually present, because for primary suffix is basically the parent chain. That is, if you consider the corresponding parent alkane, the number that you get, that is ANE, that is actually the primary suffix, and secondary suffix is the actual functional group. So look at the first example. This example you have already seen. Both sides of carbonyl you have 2 pH. So here this is the common name mostly used. Diphenyl ketone, this is also common. But diphenyl methanol, at the end the name that is given, that is actually iopap. So here the prefix are, you have 2 substituent, 2 phenyl, so that is, it is diphenyl prefix. Then the root word is single carbon, meth. Primary suffix is basically ANE, but here there is a slash mark on E because E is not written, it is omitted, but instead you write ONE. Similarly, the second example, you have both keto group as well as aldehyde. So aldehyde is getting more priority. This is 1, 2, 3, 4, 5. So 3 position you have keto group. So that is why it is 3-oxo prefix. Root word will be pent because total number of carbon in the longest chain is 5 carbon. Then again primary suffix, it is the N because it the corresponding alkane it is N, and secondary suffix is L. Fine. So 3-oxo pentanal because E is not written. Here we have aromatic ring with which aldehyde group is attached, but we also have CO2H group. Okay, so when it is CO2H group, now suffix will be different. Here the suffix is oic acid. If you compare priority of CHO group and CO2H, though we have not discussed the rules for CO2H, that will be discussed separately after finishing aldehyde and ketones. But remember, when it is acid, it is getting more priority, so that is why you are not ending the name with Al, but you are ending it with oic acid. And now the CHO group is actually prefix, and when it is prefix, it is not Al, now it is formyl. Remember, when we consider keto group as prefix, it is oxo. When it is the highest priority, it is ONE. Just like that, when it is aldehyde, treated as prefix, the term we use formyl, but when it is the highest priority group, we use the term Al. So in this case, it is not highest priority, it is considered as prefix, so that is why it is 2 formyl. Next molecule. Okay, here root word is benz because here you cannot say it is the longest chain, it is basically benzene derivative, so that is why benz and no primary suffix. Next example, here we have 5-membered ring, and in the ring we have C double bond O, 2 double bonds and methyl group. Here it will be considered as cyclic ketone, and remember, for cyclic ketone we have to use cyclopent, but it is not that cyclopentane that you will use when it is diketone, but here it is mono. So cyclopent, but you have to mention the position of the double bonds. So this is 1, this is position 1, this is 2, this is 3, that is 3 position methyl. Then the second double bond is starting at 4, and finally 5. Okay, so the position of the double bonds, first double bond is starting at 2, second double bond starting at 4, 2 for di-in, then 1 O, and 3 methyl is prefix. So root word is cyclopent, primary suffix 2 for di-in. In this case, it is not ANE, which is basically for alkane, but now it is alkene. So that is why 2,4-diene, but the last E is not used. You can see here, last E not used. After it, you have to write 1O. Aromatic ring aldehyde, it is normally called benzaldehyde, the common name, but IUPAC name, which is hardly used, phenyl methanal. So it is single carbon, meth, which is the root word, primary suffix an, and this phenyl group is considered as substituent. So that is why phenyl. Phenyl, don't need to write position of phenyl because there is only one carbon, and methanal, methanal. Then acetone. This is common name. This is also common name, but this will be the IUPAC. Propanone, or you can also write 2-propanone. Both are fine. Prefix, there is no prefix. Root word is prop because it is 3-carbon chain. Parent alkane ane, E is not written. Then after an it will be on, one. Then we have mesithyl oxide, which is the common name for this molecule. But here we will see how we are getting the IUPAC name. So I will write the structure here. C double bond CH, then CO, CH3. And this side we have 2 methyl groups. Okay. So this is the structure. And numbering will be starting from this position 1, 2, 3, 4, 5. So it is actually 5-carbon chain. So that is why root word is paint. There is one substituent phenyl at 4 position. So 4-methyl paint, and here primary suffix is not N, it is not alkane, it is alkene. 3-ene, but last T is not used. And 3 position the double bond is starting, that is why it is 3-ene. And 2 position 2-O. So 4-methyl paint 3-ene 2-O. Next molecule, one side phenyls, other side methyl. So common name is methyl phenyl ketone, but mostly we use the other common name, which is acetophenone. But what about the IUPAC name? This example also we have seen, but now you can break how we are getting actually the IUPAC name, that you can see in the individual column, all are mentioned separately. Here the prefix is, that is the substituent is phenyl, which is at 1 carbon, and the second carbon CH3. So it is actually 2-carbon chain. So that is why root word is eth, ETH. There is no double bond, it is alkane derivative, and one position, that is the C double bond carbon. So that is a 1. So name will be 1-phenyl ethan hyphen 1-O. Fine. Some more examples we'll see. Now these are very simple structure, but still we'll see how we are getting the IUPAC name. So when it is common name for HCHO, which is the simple aldehyde possible, H C double bond O. So we know when it is aldehyde, CHO group must be there, but other side you can have the minimum substituent that is possible is single H. So this molecule common name is formaldehyde, but if you write the IUPAC, now it will be methanal, and the reason is there is no prefix. Root word is single carbon, so meth, it is alkane derivative, that is methane derivative you can say, but A and E will be replaced by L, methanal. But we call this molecule mostly as formaldehyde, not methanal. So as I have said, for simple structure of ketone or aldehyde, mostly common names are used. For large structure, IUPAC names are used. Now the next aldehyde that is possible, if you replace this H with methyl group. So now you have methyl group 2, that is carbonyl, one side H obviously because it is aldehyde, other side methyl. Common name is acetaldehyde, but IUPAC name is ethanol. Here also there is no prefix. 2 carbon, eth, ANE, E replaced by L, ethanol, just like methanol. Third example, common name is acrolein. Now it is not just that we have increased one more carbon if you compare with the previous example, but there is also CC double bond. So now the primary suffix will be in, and the position of in is, this is 1, this is 2. So double bond is starting at 2 position. So it is 2 in. Again, no suffix, no substituent. Root word 3 carbon chain, and this is Al. Prop to NR. Okay. Now one more carbon is increased. Just compare third example with 4. This carbon 1H as if replaced by methyl. But this methylity, it will be treated under longest chain. So it will be 1, 2, 3, 4. 4 carbon chain. Root word is but, no substituent. It is alkene derivative, 2 in. 2 is the position of double bond. So but 2 in, En, no E next, then Al. Fifth example. Now we have 2 OH group and 1 CHO. But when you have OH group and CHO, CHO will be getting the priority. So these two group will be treated as substituent. So now we have prefix. Unlike the previous 4, now you have prefix, right? And the position of prefix 2 and 3. And it is 3 carbon. So prop AN, there is no double bond. AN and N, but no E. E is replaced by Al. Here we have ketone, C double bond O, but we also have CC double bond. But CC double bond, that will be treated as primary suffix. This is 1, 2, 3, 4, 5. So 4 is the position of double bond. So 4 pentene, you can also write it as pent 4 in 2 on. That is also fine. This is also okay. 4 pentene, TEN, but last T is not used. Directly after that hyphen, then 2 on. Second example. Now it is just like the first example, only difference is one methyl group is extra, but now the longest chain, sorry, it is aldehyde, it is not ketone, so we cannot compare with the previous one. See, this is aldehyde, this is 1, this is 2, 3, 4, 5. So the position of double bond is 3. So 3 pentenyl. Trans is used because the two groups are opposite to each other, and the two hydrogens that are opposite to each other. So you can write trans or E. So these are the position of hydrogen. And the large group, this is large group, this is large group. If you across the CC double bond, they are opposite to each other. That is why trans or E. 3 pentenyl. Okay. You can also write pent 3NL. It is up to you. Both are okay. Third example, this is also aldehyde. And second and third examples are almost same. Only difference is now you have one methyl group as substituent at position 3. So now in this molecule, the double bond position, that is also 3 methyl, this is also 3. So 3 methyl, 3 pentenyl. Trans is already there. So compared with this name, it is just same as the second one. Only difference in between trans and 3 pentenyl, now you have written this term extra. Fourth example, again ketone. 2, 3, 4, 5, 6. To 3 position is the position of keto. So it is 3 on, longest chain 6 carbon, 5 position bromine, and double bond position 4. So 5 bromo, 4 hexene, 6 carbon, but last T is not used. Instead we have written hyphen 3 hyphen ONE. Okay. So here remember, if you, I will also show you the opposite direction if you do the numbering. Suppose you have numbering like this, 1, 2, 3, 4, 5, 6, and you can say that in this case the position of bromine is 2, position of double bond is 2, position of carbonyl is 4, so it is giving you 2 plus 2 4, 4 plus 4 8. But in this case, if you add all this, it is greater than 8, right? But still the previous that is positions are correct. Why? Because before going, that is it is true that you should add all these numbers and check whether it is giving you lowest number possible, but that you will do only after first writing the position of ketone. So you should do the put the position of carbon in such a way so that ketone is getting as lowest number as possible, and that is possible only you do this type of numbering. So don't just follow the rule that you have to add the number and follow that one which is giving you less summation, less value. No, that is not correct. First you have to write, that is you have to recognize which is the highest priority. So here obviously C double bond O highest priority, that group should be given lowest number. After that you do the summation. So that is why it is 5 bromo 4 hexene 3 on. And why it is Z? Because here if you compare the groups, bromine and methyl, these two group, if you consider, bromine wins over methyl, and the other side H obviously less priority compared to CO, CH2, CH3. So both the large groups are same side, that is highest priority groups are same side, that is it is Z. Then the fifth example, we have hydroxy and aldehyde, but aldehyde will be given highest priority 1 2 3 4. For hydroxy, this is prefix, then but AN, no E, just write AN. 1 2 3 4, just like before, only you have methyl substituent extra at 3 position. 4 hydroxy 3 methyl, H comes before M. Okay, that is why it is written first. Then the next one, we have keto group and OH, but this is 1, this is 2 3 4. So 4 hydroxy 2 butanone, longest chain 4 carbon, BUT, but, and AN, but no E, just write ON. Next example, it is symmetrical structure, whatever direction you can choose, it doesn't matter anything. 1 2 3 4 5, if you do the other way around, that is also same. So at 1 position and 5 position you have 2 hydroxy, that is why it is 1,5-dihydroxy. 3 position, the position of on, 3 pentanone. Okay, so this is the nomenclature for the last one. So remember here OH group is getting less priority than CO, that is why it is treated as prefix. But if OH is highest priority, in that case we use the suffix for OH, which is all, OL. But now in this example it is not suffix, it is having lesser priority, that is why it is treated as substituent. So we are using prefix, which is hydroxy. Okay, so we'll see some more nomenclature problems in the next class. We are ending the session here. Thank you for listening.